Okay, so now we're going to talk about complements and the probability of at least one of something. So let's suppose that we want to find the probability that amongst three children there is at least one girl. In such a case, the meaning of the language must be clearly understood. At least one means either one, two, or three. So at least one means one or more. Now, the complement of getting at least one of anything is to get none of that type of thing. So the complement of having at least one girl, the opposite of having at least one girl, is to have no girls at all, basically to have all boys. So what we can do is we can use this procedure here anytime we're asked to find the complement of at least one of something. All right, the first thing we'd have to do is we'd label event A as the probability of having at least one of those things. And a complement then, a complement would then be the probability of having none of those things. So if we call event A having at least one of something, then A's complement would be having none of that thing. We're going to calculate the probability of having none of those things, and then we're going to subtract that number from 1. Because if you remember, the probability of a complement is 1 minus the probability of the event. So let's take a look at this example. A statistics student plans to use the TI-84 plus calculator on her final exam. From past experience, she estimates the probability to be 96% that her calculator will actually work. So there's a 96% chance that her calculator will work, which means there's a 4% chance it will not work. Because the final exam is so important, she plans to use redundancy by bringing in two calculators. And what the question is asking is, what is the probability that she will be able to complete her exam with a working calculator? So what they're asking for is the probability that at least one calculator works. That's what they're asking for. So actually, rather than going straight to the probability, let's go ahead and do this. Let's just call this event A. We'll call this event A. That's what it says to do up here. Use the symbol A to denote the event of getting at least one. So A now denotes the probability of getting at least one working calculator at the end of the test. Number 2, step 2 says let a complement represent the event of getting none of the items. So A's complement is no working calculators. So no working calculators. Okay, now the next step is to calculate the probability of none of the outcomes results in the event. So we're looking for the probability of A's complement. That's what we're going to do. The probability of A's complement. So since we're looking for none of the calculators to work, and there are two calculators, well, the probability that the first calculator does not work is 0.04 because the probability of it working is 0.96. So the probability of it not working is 0.04. So there's a 0.04 probability that the first calculator works. Now, we're going to multiply that because we're using the AND rule here, the multiplication rule. We're going to multiply that by the probability that the second calculator doesn't work. Now, these two events are independent because the first calculator working has no bearing on the second calculator working. So the probability of the second calculator working is also 0.04. So that the probability of neither calculator working is just going to be this product, which is zero point zero 0.04 times zero point zero 0.04 yields 0.0016. All right, so we have 0.0016 as a probability that none of the calculators work. So that's The third step was to calculate the probability that none of the outcomes result in the event being considered. Now, number 4 says to subtract the result from 1. So it turns out that the probability of at least 1, which is the probability of A, exactly what we're looking for, is equal to 1 minus the probability of A's complement, which in this case is 1 minus 0.0016. And when we do that calculation, we get 0.9984. All right, so the next thing I want to look at is the definition of the conditional probability. Now, a conditional probability of an event is the probability obtained with the additional information that some other event has actually occurred already. So this is how we denote it, the probability of the probability of B given that A occurs. So this is the probability of event B given that event A has already occurred. Now, the probability of B given A can be found by dividing the probability of event A and B both occurring. Actually, that's the way we use the probability of A and B in section 4.3, not the way we use it in section 4.4. This probability of A and B is the probability of A and B on the same trial. So both occurring on the same trial. Okay? This is the sense in which we used it in section 4.3. And the denominator is just the probability of A. All right, so let's go ahead and use this formula to calculate a conditional probability. All right, so here is table 4.1, the table from the first page of this section, of this chapter actually. And what we have here is the results of a polygraph test. So in each row, we have people who got a certain kind of test result. The first row is a positive test result. So the polygraph said that these first row of people actually lied. The second row is a negative test result. So the polygraph said that this row of people told the truth. Now, the polygraph doesn't know whether the people is lying, whether the people are lying or telling the truth. So the columns actually represent the actual reality. So these 15 people had a positive test results, meaning that the polygraph said they lied, but they actually did not lie. So that's what you call a false positive. The polygraph test is indicating that those 15 people lied, but they didn't actually lie. All right, over here we have these 42 people. The polygraph test actually said they lied, and they actually lied. So you see, each column represents the reality, and each row represents what the polygraph test says. All right, so let's take a look at this example, number 20. So what number 20 says is, refer to table 4.1, that's the table we have above there, and assume that one of the 98 people, one of these 98 test subjects is randomly selected. And we want to find the probability of selecting a subject with a negative test result given that the subject lied. So basically, we're basically looking for the probability of getting a false, what's this? The subject actually lied, and it's a negative test result. So that's a false negative. So let's see here. What does this result suggest about polygraph tests? So what we're going to do is we're going to label our events. We're going to let event A, we're going to let that be the event or the outcome that the subject lied. And we're going to let event B be the event or the outcome that we had a negative test result. And what they're asking me for here is the probability of a negative test result given that the subject lied. So that's how we translate it to the probability notation. And this is equal to the probability that the person lied and had a negative test result. So those are all the people who lied and had a negative test result. Let me see, how many people is that? These are the people here who lied in this column, and down here we have the 9 who actually had negative test results. So they lied and beat the test. And in the denominator, we're going to have the probability that the subject lied. Probability of A. Let's see, how many people lied? Well, that's an interesting question. Well, you see, this entire column of people lied here. So there's no single number in this table to represent all the people that lied. What we have to do is we have to find the sum of this column. And it turns out that there are 42 plus 9, 51 people total who actually lied. So now we are going to find this probability. All right? So let's see. Let's give ourselves some more space here. All right, so what the rule says is that in order to find the probability of B given A, what we're going to do is we're going to take the probability of A and B, which remember, A and B were those 9 people who lied and got negative test results. So that's 9 out of 98. And we're going to divide that by the probability that somebody actually lied, the probability of A. Well, how many people lied? 51 people lied out of a total of 98. So we reduce this, we flip the bottom fraction and multiply, and we get 9 out of 51, because the 98s actually cancel upon flipping and multiplying. And 9 out of 51, let's see, let's do that division. 9 out of 51 is approximately 0.176, or 17.6%. Almost 18% of the people who actually lied beat the polygraph test. So the last part of this question reads, what does this result suggest about polygraph tests? Well, I mean, it doesn't suggest that they're extremely accurate, because almost 20% of the time you can actually be lying and beat the test.